All right, welcome to The Explainer. We spend all day online, but have you ever stopped to think about how your data physically gets from your device out into the world? Well, today we're peeling back that very first layer of the internet to find out.
It's something we just take for granted, right? Before you can stream a show, browse a website, or even just connect to Wi-Fi, this really fundamental process has to happen. It's the magic that turns the digital ideas on your screen into actual physical signals that can shoot across cables or fly through the air. And the answer to how that happens? It's all right here, in what we call the network access layer. Honestly, this thing is the unsung hero of the internet. It's the crucial bridge between the logical world of your software and the physical world of hardware. It is, without a doubt, the true foundation of all connectivity.
So here's what we're going to cover. First, we'll break down what this layer actually is. Then we'll look at local identity, how your devices get their unique names using MACs and frames. We'll also figure out how they find each other with something called ARP. Then we'll touch on the big two, wired versus wireless. We'll get into some advanced rules like VLANs and MTU, and finally, we'll wrap it all up to see how it's the foundation of, well, everything. Sound good? Let's dive in.
All right, Section 1. What is the network layer? So what's its job, really? Well, you can think of it as the place where the digital rubber meets the physical road. It's all about making the connection real. This layer does a ton of heavy lifting. It's in charge of generating the actual electrical signals on a copper cable or the radio waves for Wi-Fi. It manages the unique hardware addresses, the MAC addresses, that are like a fingerprint for your specific device. Plus, it packages up all your data for its local journey, and even does a quick check to make sure it arrives without any errors. Pretty important stuff, right? Now, if you're familiar with the OSI model, you might be thinking, wait a minute. And you're right. The TCP IP model kind of simplifies things here. It takes the OSI model's physical and data link layers and just smooshes them together into this one network access layer. And honestly, it makes a lot of practical sense, because think about it. You can't really separate the physical medium, like a cable or a radio wave, from the rules that say how to use that medium. They're two sides of the same coin, working together for that final hardware-level delivery.
Okay, Section 2, local identity. So for any devices on the same local network to talk to each other, like say your laptop trying to talk to your printer, they've got to have a way to uniquely identify one another. Simple as that. And the solution to that problem is the MAC address. The best way to think about it is like a permanent physical fingerprint for your device's network card. It's literally burned into the hardware at the factory. And unlike an IP address which can change all the time, this one is for life.
But just having a fingerprint isn't enough. The data itself needs to be put into some kind of package before you can send it. And that package, that something, is called a frame.
Let's break down what goes into a frame. The postal envelope analogy is perfect here. You've got the destination MAC, which is the local to address. You've got the source MAC, the from address. Then there's something called ether type, which is like a little note on the envelope saying what kind of data is inside. Is it an IP4 packet, an ARP request? Then you've got the payload, which is the actual letter, the real data. And finally, you have the frame check sequence, or FCS. That's like the wax seal on the envelope. It's there to make absolutely sure it wasn't opened or damaged along the way. All right, Section 3, finding your neighbors with ARP. This is where we hit a really critical problem. The huge global internet runs on logical IP addresses to get data from, say, New York to Tokyo. But your tiny local network, it runs on these physical MAC addresses just to get data from your computer to your router. So you've basically got two totally different languages being spoken at two different layers of the network. The IP address is for the long, global journey. The MAC address is for that final, local delivery, the last few feet of the trip. So the million-dollar question is, how do we bridge that gap? How on earth does your computer translate a command like send this to IP address 192.168.1.10 into, okay, I need to send this to the specific device with the MAC address 00.1a.c2.7b.00.47? Well, the solution is this really clever translator called the Address Resolution Protocol, or ARP. It's simple, but it's brilliant. Imagine your computer, computer A, basically just shouts out to everyone else in the room, the whole local network. Hey, who here has this IP address? All the other devices hear it, but only the right one, computer B, raises its hand and replies, oh, that's me. Here's my MAC address. Then computer A jots that down in a little notebook. It's cache, so it doesn't have to go around shouting again next time it needs to talk to computer B. Okay, let's move on. Section 4, wired versus wireless.
let's talk about the actual physical highways our data frames travel on. And really, there are two main ways this happens: the classic Ethernet cable and the invisible radio waves of Wi-Fi.
And looking at these two really highlights a fundamental trade-off we all make every day. On one hand, you have Ethernet. It's the wired standard, and it's all about rock-solid, predictable, high-speed stability. On the other hand, you have Wi-Fi, which gives us that amazing flexibility and mobility we love. But that convenience comes at a cost. Because everyone is sharing the same invisible airwaves, devices have to be really polite. They have to carefully listen to make sure no one else is talking before they start, to avoid signals colliding and creating a mess. It's a clever system for keeping the chaos organized.
All right, Section 5, let's get into some advanced rules. Now that we've got the basics of addressing and transmission down, let's look at two, let's call them rules of the road, that make the huge, complex networks we use today even possible. So, first up, there's a size limit. Just like a bridge has a weight limit for trucks, a standard Ethernet frame can't be bigger than 1,500 bytes. This is called the Maximum Transmission Unit, or MTU. It's basically the maximum package size allowed on the data highway.
So the obvious question is, what happens if your data packet is bigger than 1,500 bytes? You can't just throw it out, right? Well, the answer is something called fragmentation. The network is smart enough to just chop that oversized packet into smaller, MTU-friendly pieces. It sends them all individually, and then the device on the other end perfectly reassembles them, like putting a puzzle back together.
Okay, next up, VLANs. I want you to picture a huge office network, right? Hundreds of computers, printers, servers. It could be chaos. To keep everything organized and, more importantly, secure, you can use something called virtual LANs or VLANs. They let you take that one giant physical network and logically slice it up into multiple, smaller, totally separate virtual networks.
So how does this work? It's actually pretty cool. A little digital tag gets added to each and every frame. This tag tells the network switches which virtual network that frame belongs to. So for example, a frame from someone on the engineering VLAN literally can't be seen by any devices on the marketing VLAN, even if they're all plugged into the very same physical switch. And this is just absolutely essential for big networks. Why? Well, two big reasons. First, security. It stops the marketing team from accidentally stumbling onto sensitive engineering servers. And second, performance. It keeps all the network chatter from one department from slowing everyone else down. It's digital organization at its best. So let's bring this all home. Section 6, the foundation of connectivity. Let's tie this all together and really see why this layer is the absolute foundation of, well, everything we do online. Think about your day. Every single time you connect a device to, well, anything, you are using this layer. When you connect to your Wi-Fi at home, that's the network access layer. When you plug in an Ethernet cable at the office, yep, that's it too. Firing up a mobile hotspot on your phone, you guessed it, you are relying every single time on the protocols and the hardware of this layer to make that initial handshake, that first connection, happen. So, what's the big takeaway? The network access layer is the physical foundation of our entire digital lives. So, what happens when that foundation fails? It's simple. Everything stops. It's the indispensable first step for every single packet. It's the physical reality that holds up our digital world. Without it, without its MAC addresses, its frames, its physical signals, the internet just ceases to exist. There's no cloud, no streaming, no connection, nothing. It's a pretty powerful reminder that all of our digital magic, at the end of the day, still relies on a tiny signal traveling down a wire or flying through the air. Thanks for watching.